Okay, my talk devoted to review of two-phase emission detectors, research and development, which actually have 50 years of history at this year. And this talk actually devoted to the memory of great scientist Boris Anatolyevich Dolgoshein. In his laboratory, I started my career also about 50 years ago. And at this first slide, I show his forward to first book devoted to technology of emission two-phase detectors, which he signed in 2009. And he said at that time that 40 years ago, at that time it was really 40, now 50, a group of Russian physicists investigating electron emission from liquid argon were able to formulate the unique properties of a new detector technology that could be developed employing this effect. They called these detectors emission detectors. Emission detectors seem to have found their niche in low background experiment search for cold dark matter and low energy neutrino interaction. The further development of this interesting class of radiation detectors may enhance the arsenal of modern physical methods and other exciting fields like the neutrino-less double beta decay search, solar neutrino physics, and possibly in many new areas that cannot be satisfactorily served with existing detector technology. And this year also we celebrate 90 years of this great physicist, and I'm happy that I have a chance to mention about this event in my presentation. Back to 50 years ago, in laboratory headed by Boris Anatolyevich Dolgoshein, his PhD student Boris Rodionov and graduating student Vadim Lebedenko investigated liquid argon like a possible medium for streamer chamber. I would like to actually note that by that time, laboratory headed by Boris Dolgoshein developed and built biggest streamer chamber in the world. It was 8 meters long streamer chamber. It was designed and constructed at MIFI, Moscow Engineering Physics Institute, and with particular goal to find out W boson. And detector was installed at later at in 60s, I would like to say, at Serpukhov accelerator. At that moment, it was biggest accelerator in the world, and with hopes that they, using this streamer chamber, discover the W boson. Unfortunately, it's not happened just because, as we know, that mass of this particle was slightly larger than energy of proton accelerator built in Serpukhov. Anyways, streamer chamber had a great history. They investigated, they measured the polarization of muons, investigated more other physics. And at that time, they start to think about development of this technology in direction to increase density of working medium with the attempt to detect low ionizing particles and detect complicated events, including gamma rays and others. So on this reason, there are two ways to solve this problem. One way is try to build a streamer chamber with spark discharging along the tracks in very dense medium, like liquid noble gas, or another approach that to use low temperature with normal pressure, but because of low temperature, increase the density. The second way was developed in ITEP, in the laboratory headed by Lyubimov, but Dolgoshein and his young colleagues developed the way to detect particles in liquid argon first. And they discovered unexpectedly, by the way, that ionization electrons can be extracted from liquid argon, like shown in this picture. For example, using a structure like that is cathode, anode, gate between them below the surface of the liquid. And if we have ionization here, like from sharp needle, shown here, or alpha particle source, which produce ionization in liquid, and then we have applied electrical field between anode and cathode, and these electrons come to the gas. And in gas, we know how to detect electrons and how to detect tracks of the high energy particles. That was the idea. And they built the first device in this approach was built in 1973. It was liquid argon spark emission chamber. So the design of the detector shown in this left picture. So we have cathode with alpha particle installed in on this surface, and covered with liquid with cathode, which could be in the gas phase or could be even also in the liquid. You can measure ionization current, for example, and specify the effective ionization yield from tracks of alpha particles or whatever particles you use. So in this right picture, you may see the picture, actually distribution of alpha activity over the source installed to the center, in the center of the chamber, not like here shown on the side, but in the center of the cathode, like here. So, and you may see that there is a cathode which built from many wires, and each wire actually placed in cathode placed in the gas in this specific experiment. And when electrons extracted in the gas phase, they can generate spark discharge in nearby the wire. Many of these sparks actually form activity of alpha source. So the ring around, that is effect of shape of the cathode. Cathode has a kind of actually has curved inside the position of alpha source, and this curve reflected the light of all the sparks and formulate this nimb around the alpha source, but it is actually just effect of configuration of detector. Most important that we can see the alpha particles like intensity of this light proportional to activity of ionization. So that is what first emission detector, which allowed to visualize the distribution ionization particles on the surface of the, in this case, alpha particle. So this first publication in Jet Letters in 1970. So we consider this publication like first publication related to two-phase emission detectors, like we call them now. So The next step in this direction was to follow idea to build a streamer chamber. But in this, after this discovery that we can extract electrons much easier to extract electrons and or track of ionizing particles from condensed noble gas in gas, and in gas to have just a mode of normal streamer chamber. So you have anode with high voltage pulse source, which applied when particles come through the layer of noble gas, condensed noble gas, with delay needed to extract electrons in gas phase. And this narrow gap above the condensed phase, we have generated the track of particles. It was very nice tracks, very dense, with very small sparks, streamers. It formed a very like continuous track. Also, this device shows that we can detect interaction of particles, high energy particles. On the bottom picture, you see the particle, in fact, it comes from this side, interact inside the condensed noble gas, and then products of this interaction, like many tracks of particles, pass through the condensed noble gas medium and left the short tracks over here. So because the layer was pretty thin, about 5 millimeters, an experiment was established at ITAP, synchrotron accelerator, proton accelerator at secondary beam, when the pions come through the detector and their position selected with scintillation counter. So that is normal configuration for high energy experiment. So when particle comes through the detector, the trigger system generates the high voltage pulse, and we, after the delay for drift electrons in their emission, we generate the track. So this idea was pretty good working. Unfortunately, it was understood, and actually later this principle was built big emission streamer emission chamber based on liquid krypton, because we didn't have xenon enough at that time. We call this detector HOP, or Nadezhda in Russian. So that picture of this device shown here. So the streamer chamber above the liquid tank is liquid, about 15 centimeter and about 50 centimeter diameter. High pressure generator, pulse generator, which applied high voltage pulse in this two-gap gas area. And when electrons come through the liquid, we can generate a streamer track. This device was pretty big for that time, and built it just before very difficult times for our science in Russia. But anyway, it was tested with laser. Streamer chamber was working, and it's shown this track from laser in neon gas with addition some low ionizing vapor. And also bottom part also was tested with thick layer of liquid krypton. It was measured efficiency. It actually was very big at that time device for to make electrons effectively drift and emit in the gas phase. Unfortunately, the device was not finished in testing at the beam, because actually all scientific activity at that time stopped at ITAP. But anyway, it was shown that we can built like this chamber. In parallel with development of track detectors, was very big efforts to investigate possibility to detect electrons extracted from the noble gas and other condensed dielectrics media by electric field and effectively detect them. So not only in Russia, also in France, Lancier, Signer, and Moretti, they also investigated possibility to build a two-phase detector with extraction electron in gas phase and detection with photomultiplier electroluminescence flash in the gas phase. In Russia, in actually joint efforts, MIFI and ITEP was built very small chamber with working volume about 1 cubic centimeter, which can be filled with different liquids, solids, krypton, xenon, methane, their mixture, and others. With PMT, we can through the glass walls what happened inside, and we can see first scintillation when alpha particles activate the condensed working medium, and after drift time, electroluminescence flash when electrons drift through the gas. With this detector was investigated efficiency of electron emission and different media, like I said. Plus, it was shown that using in this work and in this work, we can use photomultipliers and detect two signals: scintillation, which happen in the moment of interaction radioactive particles with medium, working medium, and delayed, but also actually associated with this event, electroluminescence flash, which was much more intensive, will allow to exactly very to measure number of electrons we have extracted. Okay, so using this idea was built multi-channel detector, which called emission gamma chamber. And this device was built also in joint efforts, MIFI, ITEP, and VNIM, that is Institute of Medical Devices. So this device actually very nice example. That is actually a prototype of all two-phase emission detectors based on xenon and argon, which is working right now. So we have, at that time, it was very thin layer of liquid or solid xenon on the top of bottom of the detector, and not gridded electrode above, an array of PMTs installed through the windows above this medium, and that allow to detect, for example, gamma rays. That is actually image of the lead mask with holes, which was placed in front of the detector with the gamma source, which was cobalt placed below the detector. So we can see that the device has position sensitivity and quite a large area. It was tested with solid and xenon and liquid xenon, and proposed to use for nuclear medicine for imaging of gamma ray sources inside the human body. And this actually idea about this time, first paper was published about possibility to search for dark matter using two-phase emission detectors. But at that time, because masses of particles which can be candidates for WIMPs considered in the range of 110 GeV, for working medium was proposed to use liquid isooctane, that is saturated hydrocarbon, which work at room temperature and provide pretty good gas gain for electrons extracted, about 10 to the 4. And so it was proposed to use for detection of dark matter. But soon after that, actually in 15 years, it was clear that dark matter should have more heavy particles, and this direction was forgotten. Instead of that, intention was returned to xenon, and this example of using xenon, which utilize two signals: scintillation in moment of interaction, radiation with working medium, and electroluminescence flash after electrons extracted in the gas, with a position-sensitive array of PMTs installed above. So we can see that the distribution, that also image of lead mask with holes, regular holes, irradiated from the top with energy 122 keV. And you can build not only XY distribution, but also Z distribution. For every point you see, you can measure not only position in the area of the sensitive area of the photomultipliers, also position in the depth of the detector. So 3D positions detector. It was very exciting result. It shall allow for nuclear medicine speak about possibility to build Compton camera. Compton events shown over here. I will not time to discuss about this, but that is very interesting approach. Actually, was protected by patent in the United States. And at that time, we understood that if you use liquid xenon in a large volume and use two signals, scintillation and electroluminescence, like I described, we can build device which can select event happen inside the detector. So we so-called wall-less configuration, so we can avoid background associated with radioactivity of surroundings, walls of the detector, surround the material around the detector. So we can select events in the central part because of 3D sensitivity with like this technology of detection. And it was proposed at 1995 to use this technology for detection with very high sensitivity to electrons, down to single electrons, with effect of cell screening from background to search for rare events and weakly interacting particles, starting from neutrino and dark matter also was mentioned in this work. And in fact, that was this development opens the way for development of high two-phase emission detectors for dark matter search. I will not stop very detail because of limited time on all this development. That one of the first detectors, this kind, xenon 10, this first result, real result shown here with scintillation S1 and electroluminescence S2 signals with 3D position sensitivity. This allows to have a large enough detector, like about ton. We can very effective shielding from neutron background, like shown in this picture. So, and this was very exciting time. And actually, after that, a number of detectors of this kind was built over the world, starting from xenon collaboration, Zeppelin collaboration in England, LUX in the United States, DuckSight in Italy, collaboration working in Gran Sasso, in China, Panda X device, and this device actually all this direction now leading in best limits for possible mass of the dark matter particles in form of weakly ionizing particles, WIMPs. And the best actually device which is close to actually start working now, that is LZ, joint collaboration Lux and Zeppelin, which already use 7 tons of liquid xenon. We probably know, will not talk about details. We know about this pretty well. Eventually, we have limits for existing of WIMPs in scale of cross-section and mass, which if that is limits given different experiments. And we see that the last prediction all given by two-phase emission detectors. And what is interesting, all this prediction approaching to point when this kind of detectors become sensitive to solar neutrino coherent scattering. So if we go with larger mass detector, so this will be irreducible background, and actually eventually this kind of detectors become not dark matter detectors but solar neutrino detectors. Okay, and now we have already a couple direction to use this technology for neutrino physics. One of this direction actually developing it MIFI in cooperation with Kurchatov Institute, Dubna, and others. And this now experiment, which actually use the detector RED 100, two-phase emission detector with liquid xenon, 200 kilogram of liquid xenon, going to be installed at the Kalinin nuclear power plant, unit 4, next year. So by end of this year, the installation should go to the Kalinin nuclear power plant, and that is configuration. Detector actually inside the passive shielding, water and copper, looking like that, installed under the nuclear reactor at Kalinin power station, 19 meters distance. And that will be experiment for neutrino relatively low energy, because all coherent scattering now actually observed with neutrino with energy about 50 MeV. And now we go to see effect at pure electron antineutrino beam at energy few MeV. Actually, a cost for high cross-section, which allow to use relatively small detector to detect this kind of neutrino, is very small signal, which consists of few electrons, like 2-3 electrons per event when neutrino coherent scattering on nuclei of xenon. So this detector assembling in a clean room in MIFI. So, and another very interesting approach, which that actually experimented observation of high energy neutrino oscillation generated at Fermilab accelerator, passing the way 1,300 kilometers to Sanford underground research facility, detecting in here there is a first particle detector at entrance beam in the Earth, and secondary detector on the ground located, which actually should be 10 kilotons two-phase emission, actually liquid argon TPC. One of them suggested to be two-phase emission with amplification of signal with GEM gas electron multiplier. So that is huge detector which you can see the figure of people over here next to this device. And but that is actually planned in reality at CERN. Now we're already on the way to test 6 by 6 cubic meters, so 300 tons liquid argon two-phase emission detectors. That this picture is also figure of people to compare the dimension and how it looks inside now. So that is very exciting project, and actually gold not only observe neutrino oscillation, but also proton decay and probably detection of astroparticle, astroneutrino. So at my conclusion, and so what we have in this story is that two-phase emission introduced in experimental practice 50 years ago in laboratory headed by Boris Anatolyevich Dolgoshein. Over 50 years development pass away from miniature detectors with working mass about 1 gram to multi-ton detectors for solving fundamental problems of modern physics. So I actually, when I calculated the number, I was in shock. So mass of the detector increased like in 10 million times, and we can work with them, and including experiment of the second generation to search for cold dark matter, which actually use about 10 tons of liquid xenon, and actually plan to have G3 generation of dark matter detectors of this kind of two-phase with mass up to 200 tons using liquid xenon or liquid argon like working medium. And example of proto-dune double-phase prototype is largest emission detector ever built. It's already impressed with mass, and actually at the next, if all technical problems will solve successfully, we're talking about building huge, very biggest detector ever built for particle physics. That is the story of two-phase emission detectors introduced at MIFI 50 years ago. Thank you very much for your attention. Please give me a question.
There is one question in chat.
Comment.
Yes. Yeah, we have a chat. We can write down the question.
Okay, so the comment is, it is necessary to stress that RED installed at Kalinin nuclear power plant could see in principle directly the plutonium accumulation in reactor core.
Yeah, that is very nice question. We believe actually that is shown by Mikhaelian and his group in Kurchatov Institute, like in past century, that if we effectively detect neutrino using the effective detector, we may control changing of isotope content of the active zone. So when plutonium-239 generated, neutrino flux changing. So if that is very important from point of view international efforts on limitation of nuclear weapon distribution, because plutonium-239 very effective material to build compact small nuclear bomb, because critical mass very small, half kilogram. So, and but there is no actually effective way to control what happens inside the active zone if this nuclear plant actually under supervision of a foreign state. With detector like this type, we can use distant monitoring of nuclear. For example, like detector like Red 100 or something like that could stay on track outside the nuclear plant and effectively detect flux of neutrino. If flux of neutrino change inappropriately, we may conclude that somebody exchanged the fuel inside the active zone and plutonium-239 disappeared. So that is effective control. Very impressed, for example, vice president of MAGATE, actually IC, International Agency of Atomic Energy, Tero Vayaranti, who visited our lab in a couple of years ago. He said that is our approach very important for international community to test independently on anybody what happened in active zone of nuclear reactor. So that is a possible application of this technology. So, okay. So if
sorry, can I also ask a question?
Yes.
Yeah. Thank you very much. This was a really interesting talk. I wonder if you can comment on the recent studies, and not so recent also, studies of xenon plus argon usage. When you dope argon with xenon and use that for discrimination, well, it's kind of the solution will save PSD properties, but you won't need shifters, spectrum shifters. So if it is if there is any pros or cons.
Well, there are many efforts in this direction. Argon, interesting medium, plus it has it can be used effectively for charge gain of signal. So for multiplication of electrons and taking not electromagnetic signal like S2, but amplified signal. In xenon, in pure xenon, it is not effectively. Less gain you can have in pure xenon vapor, like 200 or something like that, even less. So in this sense, mixture of argon and xenon is very interesting, except that argon can contain argon-40, which is radioactive, and it is not very nice. So we have used isotopic enriched or depleted argon. So that is a very possible way. I don't know, do anybody succeed with this, but in earlier stages of this development, we try to use different mixture, and that is really can work. The question is, can we build this for particular condition needed for a real experiment, like use isotopically depleted argon, for example, and what real gain you can achieve. So I don't know that this problem is effectively solved right now in metal, I mean.
Thank you.
Yeah, you're welcome.